There we go. The last quiz is optional. It's on 11.1 and 11.2. And I'll give you a chance to ask questions at the end on 11.1 and 11.2. Basically, it looks like this. So you can see the setup. So just so we understand, if you submit the quiz, that means it will be graded and it will count towards your overall quiz score and your overall grade. If you just want to click on the quiz and give it a try, or click on the quiz and ask a question on it on Thursday as part of your review for the test or whatever, that's certainly fine. Or during office hours, perfectly fine. Or even tomorrow. But if you submit it, it's going to get graded. If you don't submit it, I will mark it as an excused quiz and it will not count against you if you choose not to do it. Okay? But this quiz is basically dealt out to everybody based on the second to last digit of your student ID number. The second to last digit. So real quick, if my ID number was 3.14159, the second to last digit is a 5. So I would want to make sure I click on the quiz that says 5. Okay. I have to start getting creative with how I deal these things out. So we mix it up a little bit. So the second to last digit. Same rules as usual, but it's due tonight at 11:59 p.m. And you can access it at 10:45. So as soon as class is over. And it's just 2 problems. 2 problems. So between midnight and 12:15 on tonight after midnight, I take off 2 points because 2 points would be 10%. And after 12:15 a.m., it would be not accepted at all. Single PDF as usual, upload your quiz. This is how you want to label it. Tuesday, Thursday, quiz 11.1 to 11.2. And this is what it's going to look like. These are the directions for the 2 questions. Problem number 1. You must solve the equation by completing the square. If you do not solve by the completing the square method, you will earn 0 points. Remember, your work must justify your answer. So on problem number 1, you have to solve that question using the completing the square method from 11.1. You don't get to solve it any way you want. You have to solve it with completing the square method. Step 1, isolate the constant. Step 2, make sure it's 1 times your x squared. If it's not 1 times x squared, you divide all the terms by whatever that a is. Step 3, you take half of b, you square it, and you add it to both sides. Step 4, you factor the left side into a nice perfect square. It's either a plus b perfect square equals a number, or a minus b perfect square equals a number. And then step 5, you take the square root of both sides. Don't forget your plus and minus. And step 6, you solve for x. Make sure you simplify. Question number 2. You must solve this equation using the quadratic formula. What is A equal? What is B equal? What is C equal? And then plug it into x is equal to the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And then simplify. Step by step. If you don't solve it using the quadratic formula, you're going to earn 0 points. This is exactly how your chapter 11 test will look. The first two questions on your chapter 11 test, and let me pull that up real quick, because everybody should have gotten the review sheet, right? I sent this out on Sunday.
Oh, yes. Oh, it was on Sunday? I thought you barely gave it to us yesterday.
No, I sent it out Sunday.
Alrighty.
I sent it out Sunday night just to get ahead of the curve. That was a pun. Sent this out Sunday night. Your test is going to look like this. It's just going to be 6 problems, not 7, but 6 problems. The first 2 problems, you have to solve it using completing the square. You have to do completing the square. The next 2 problems, you have to solve it using the quadratic formula. And then the last 2 problems, it doesn't specify. You can solve it any way you want. If it factors, factoring is the quickest, easiest, nicest way to solve a problem. If you want to stick with a quadratic formula, you can solve it with the quadratic formula. If you want to solve it with completing the square, you can solve it with completing the square. But obviously, these last 3 questions are not completing the square ready, nor are they quadratic formula ready yet. And then the last 8 through 30 are examples from chapter 12. 8 through 30 are examples from chapter 12. And that test is going to be no more than, I believe, 14 problems. So this one is 6 problems, and this one's 14 problems. They are completely separate tests. They would be in separate assignments, separate downloads, and separate submittal. You know, you submit them separately. You don't submit them as one test, you submit them separately because they're going to be separate grades. That'll all get explained when you open it up on Thursday. And you would have from Thursday after class until basically 12:59 that night. Okay. Any questions? All right.
One.
What you got? I thought I heard somebody say I have one.
What happened?
I thought I heard somebody say I have a question.
Oh yeah, I was on mute. Can you show how the test is supposed to be labeled again?
Oh, this quiz?
Yeah, the quiz, how I'm supposed to name it.
The quiz is going to get labeled last name dot first name dot math 103 dot Tuesday Thursday quiz 11.1 to 11.2.
Okay, I just want to take a picture of that. Thank you.
When you open it up, it'll be there.
Oh, gotcha.
I have a question.
Yes.
When will you post the final grades?
Now, okay, so that's, I don't have to actually post final grades and have everything done until a week from Monday. So I usually tell students, do not even email me until after, so Monday the 7th, and then Monday the 14th, like by 3 p.m., you can start emailing me about grades. Now, does that mean I might have them done sooner? That could be. And I would send out the usual, hey, everybody, grades are done. If you want to email me, email me.
Okay.
Okay. One thing about these certain tests, like I will return your chapter 11 test to everybody, but I never return chapter 12 to anybody because it's always last in the semester and I just don't put it out there. But I will definitely, when you get your overall PDF score of your grade, you'll see the grade on it. And if you want to do a one-on-one Zoom, we definitely can go over it. Okay. Okay. So tomorrow, Wednesday, if you want to I'm going to send out the general invite to Monday, Wednesday's class because they're going to be reviewing before they take their chapter 11, chapter 12 test Wednesday, because they're going to do theirs tomorrow. And then you have your review and you start your test on Thursday. Your final is next Tuesday. Your final is next Tuesday, the 8th, from 8 a.m. It starts at 8, not 8:30. It starts at 8 a.m. and you have until 9:50 only. All finals, no matter what, are only an hour and 50 minutes.
How many questions are in the final
Let
exam?
me. It's a surprise. One question, just one. It's got 37 steps to it. No,
You said 9:50? It's gonna
9:50,
end?
yeah.
Okay, thanks.
All finals are only an hour and 50 minutes. So the final, I have not yet written. It'll be minimum 40 problems, maximum 50 problems, multiple choice. And it will be on Pearson. So you wouldn't even need to log into this class. You can if you want, because I will open up class at 8 o'clock in case you have any questions during the final. It's like being in the classroom. But the final will be accessed on Pearson, just like your homework. And you're going to take your test on Pearson itself. And that's basically the only way I can get a multiple choice test done, because we can't do a multiple choice test because, at home, because there's no work for you to turn into me. All you would be doing is turning in A, B, C's, and D's. And that's really easy to cheat when people are just right next to each other. So it's easy to do a Pearson test when I can scramble problems and scramble answers and scramble all sorts of things. Hopefully you like scrambled and not over easy. But again, I will remind you, and I'll send out I will send out an email probably Saturday or Sunday to remind you. And I will also send out a Zoom, a little like a YouTube posting. Here's how you take a test in Zoom. It's just like taking a quiz. You cannot print it. You're not able to print the test out. So you can use scratch paper, copy the problem down, work it out, scratch paper. Don't guess. Hopefully you're not guessing. And then once you click, move on. If a problem's too hard, move along, come back to it later. Do all the easy ones first, the ones you're going to get right, and then come back and do the more difficult ones. That way you don't eat up all your time staring at number 3, and then you look up at the clock and you only have 5 minutes left. And you have, 35 blank problems that you didn't do. So we'll talk about that. And again, I'll put together a video of here's what you want to do when you attack your final. And it covers the entire semester, which we've been reviewing all along in our bonus questions. Can you write the equation of a line? Look out for parallel and perpendicular. Oh my gosh, that keeps coming up. Horizontal and vertical lines that people keep leaving blank. I wonder why. Anyway, chapter 12, here we go. Right, chapter 12. Oh, and those of you that want your overall grade after the chapter 10 test, I return chapter 10 on Sunday. I appreciate your patience with me. I hit a physical snag last week where my body gave out and I could not grade anymore, any more quickly than I could. I was working as fast and as quickly as I possibly could, and my body just kind of hit a wall. The fact that I am able to stand today is I'm grateful for. We'll see what happens by the end of the day.
Well, I hope you feel better.
Well, thank you. I need to get to the chiropractor. So look at number 1. Chapter 12. And if you hear the strain in my voice, it's just you can picture my wife just rolling her eyes. Are you still hurting? Quit making those sounds. Sorry. No, she's actually worried, but anyway. You should be able to do 4 to the 1/2 power. What do? You got to participate, or else I'm just gonna talk, and I will go as fast as I possibly can.
You'll square root it.
You square root it. 4 to the 1/2 power means square root of 4, and the square root of 4 is 2. Now, for some reason, which was completely mind-boggling to me, what a lot of you were doing on your test had nothing to do with what I was teaching in class.
I can't see the board, Mr.
Oh,
Escobar.
thank you. So I'm going to put 2 in here. I'll show you in just a minute. This one, 16 to the 3/4. What you were doing on your test, your chapter 10 test, 16 to the 3/4. And it wasn't just one person, wasn't just 2 people. It was, maybe 2 handfuls, or a hand and a half full. Instead of doing the question like I thought you were supposed to do the question, as I would expect you to do the problem, the only way I ever presented the problem, it's like you must have been watching somebody else's lecture, and not just one person, but quite a few of you were doing it the same way. And that raises a lot of red flags. It does.
I was watching a couple of YouTube videos.
And that's perfectly fine. But the point of the whole chapter 10 was the relationship between exponents and radicals. Exponents and radicals. That idea and that notion that this a to the m over n means the nth root of a to the m, or a to the m over n is the nth root of a, the whole thing to the m. Now, I saw this be, the 16 to the 3/4. I saw this become 2 to the 4th and to the 3/4, which was, that is absolutely true. And then 4 times 3/4, the 4 is reduced. And then 2 to the 3rd is 8.
What is doggy? What's this doggy?
He's sleeping.
Okay, absolutely fine. It does work. But the whole idea is it's also the 4th root of 16, which is a perfect fourth power to the third. The fourth root of 16 is 2 to the third, and 2 to the third is 8. So I just have to put it out there. If you're choosing to cheat, and this is not an accusation, this is just a declaration. If you are choosing to put problems into the internet, like Chegg or whatever else you're choosing to do, when people have exactly the same and show exactly step for step the same work as if they were copying somebody from the board into their notes. You're not learning anything. You may think I'm getting away with something, but you're blowing the opportunity to actually learn something. And it is so freaking disrespectful to me. And all that makes me want to do is, well, I don't want to write 8 different versions of the same test again. But I don't want students to earn a grade that they didn't earn, to receive a grade they didn't earn. Cheating is not earning a grade. So I've made my declaration. And I've made my naughty and nice list. That's all. So the last answer, number 2, is an 8. I could have saved a lot of time in grading if you just would have all written your names on one version of the exam and turned that in. Okay. Real quick, if we look at the review sheet, when you get to these 3 questions, 8, 9, and 10, 8, 9, and 10 are these 2 functions, f of x and g of x. F of x is 4 to the x. G of x is 1/5 to the x, that fraction, 1/5 to the x. And you have to express it in exact value, no decimals. So this is exactly what's happening in this question right here. F of x is 4 to the x, and all they want you to do is to find f of 2. So you're given f of x is 4 to the x power. So they want you to evaluate for f of 2. So we plug 2 in for x. If we put a 2 in there, then we got to put 2 in for that x, 4 to the second. And what's 4 to the second?
16.
16. And those of you who are not, who have no guilty feeling in their bones whatsoever, I ain't talking to you. You got everything, everything's cool. Everything's good. No worries. Okay, this is where we got to be. This is where we've been. We're going to be solving something called an exponential equation. Something that looks like b to the x equals some number c. We want to know, what does x equal? Solve for x. This is where sorry, I said that backwards. I said this is where we've been. This is where we're going, solving an exponential equation. This is where we've been. We've solved linear equations. A linear equation looks like a times x plus b equals some number c. Kind of like this. Kind of like a 5x minus 2 equals 8. We've solved those. We've been solving those since Math 201, Algebra 1. And then in Math 201 in Basic Algebra. And then we just got done in Chapter 11 solving quadratic equations. Ax squared plus bx plus c equals 0. In basic algebra, we could only solve them if we could factor them. In Chapter 11, now we can solve any quadratic formula thanks to the completing the square method or the quadratic formula. We can solve any second degree equation. Any equation that is a power of 2, a second degree equation. This is linear, it's a first degree equation. It's x to the first. The only variable that we have is an x to the first problem. This is an x squared problem. 7x squared minus 8x plus 8 equals 0. We can solve that. Either we factor it, or we complete the square, or we use the quadratic formula, but we can solve it, no matter what. Now we want to solve something like 5 to the x equals 25. Look at the difference between those two types of problems, an exponential equation versus the linear and quadratic. Exponential equation versus the other two. What makes this kind of equation different than those kind?
Would it be the x?
Where the x is. Here, x is the base. X to the second. X is your base. The exponent is a 2. Over here, the exponent is your x. The base is a number. The base is a 5. That's what makes it an exponential equation, is the position of your variable. Where's your x? So this has got a completely different method for solving. You can't do that to it, where you just isolate and get x by itself, add 2 and divide by 5. There is no simple, nice quadratic formula that you have to do over here. What you have to do to solve an exponential equation is step 1, rewrite, and this is only if possible. It may not be possible. Rewrite, if possible, both sides using a common base. Common base meaning same base. The same base. So 5 to the x equals 25. Well, 5 and 25 are both powers of 5. 5 to the x, and over here, 25 is 5 to the second. They're both powers of 5. So once you can rewrite them using the same base, then step 2, once the bases are the same, you let the exponents equal each other. And solve. You let the exponents equal each other and solve. 5 to the x equals 5 to the second. So this x has to equal that 2. If these bases are both 5s, then the only way the left side equals the right side is if that exponent x is equal to that exponent 2. So you let the exponents equal each other and then you solve it. Well, I got x by itself. So I'm done. X equals 2. And that makes perfect sense. I bet you knew it a long time ago. 5 to what power is 25? 5 to the second power, 5 to the 2 makes it 25. Do you see it?
Yes.
Okay, because that's what we're after. What power turns the left side into the right side? What do I plug in here? So it's an exponent. So x equals a 2. If only they were all going to be that nice. Like this one. 243 to the x equals 9. So this is why you have a nice chart of all your powers. So what you want to do is on your list of powers, you want to find a base. So you got your bases. And on your bases, we had 1, and we had 2, and 3, and 4, and 5. And we did 1 to the first, second, third, fourth, and they're all 1. And we did 2 to the first was a 2. Well, 2 to the 0 was a 1. 2 to the first was a 2. 2 squared was a 4. 2 to the third was a 8. 2 to the fourth was a 16. Well, there is no 9 on that list. 2 is not going to give me a 9. 3 to the 0 is a 1. 3 squared. Oh, 3 squared is a 9. 9 is on 3's list. I wonder if 243 is on the same list as 9 is. And that's what you would see. 3 to the third is 27. 3 to the fourth is 81. 3 to the fifth is 243. 243 is on the same list as 3. These are both powers of 3. So this is, making some room, 3 to the fifth to the x, which you guys should be pros at because that's how a lot of you were doing your rational exponents. You were converting it into these things. So I'm looking forward to grading these tests. And 9, well, that's 3 to the second. Now you have almost ready. 3 to the 5x equals 3 to the third. Oops. 3 to the second. The same base, common base on each side, the same base. They're both 3's. Once you have the same base on both sides, you let that exponent, 5x, equal that exponent 2. And then you get to solve for x. It's 5 times x equals 2. Divide both sides by 5. So x has to equal 2/5. And it's going to be a problem where no decimals, leave your answer in fraction form. Number 7. And yeah, you can get all sorts of crazy things. 16 to the 3x minus 1 equals 4. So we want a common base. 16 and 4 are both powers of what?
2.
2 would work, but you can actually go with a nicer number.
4?
Yeah. They're actually both powers of 4, which means you have a smaller exponent to use. 2 would work, but that just means you're going to use, if you use a smaller base, you have bigger numbers to deal with. I'll show you. If I go with, I'm going to do the 4 first. If I use 4, then 16 is now 4 squared. 4 squared to the 3x minus 1. And then this is 4. Now, here's what you got to think about, though. You're going to let the exponents equal each other. So on this simple 4, what is the exponent that's right here that you don't see?
1.
Perfect. That's 4 to the first when you just have a 4 by itself. Now, what you got to remember is power to a power is multiplication. So when you multiply this, I'm going to show the extra step. It's 4 to the 2 times parentheses 3x minus 1 times that whole exponent. So you got to make sure you distribute. Equals 4 to the first. So if you want, you can let the exponents let them equal each other now, or you can do this one extra step. 2 times 3x is 6x. 2 times negative 1 is minus 2. Equals 4 to the first.
Wait, can you repeat how you got the 2?
16 is 4 squared.
Oh.
So you don't have to show the step. Just remember that power to a power, you're going to multiply. So if there's 2 things right here, you have to distribute 2 to both of them. Now you let that exponent, 6x minus 2, equal that power, which is a 1. Add 2. We get 6x equals 3. And you divide by 6. X is equal to 3 over 6 is 1/2. So X would have to be 1/2. If you decided to go with 2, then you convert both sides into powers of 2. 16 is 2 to the 4th. So this 16 becomes 2 to the 4th power to the 3x minus 1, and 4 becomes 2 to the 2nd power. Power to a power you multiply. So this is going to be 2 to the 4 times 3x is 12x. 4 times -1 is minus 4. So it's 2 to the 12x minus 4 equals 2 to the 2nd. Then you let this exponent, 12x minus 4, equal that exponent, 2. Add 4. And we get 12x. 2 plus 4 is 6. Divide both sides by 12. 6 over 12 is 1/2. So either way, you're going to get 1/2. But if you go with the smaller base, you get bigger numbers you got to keep track of. If you can use the biggest base, the largest common base possible, you end up with smaller numbers to work with. But that's, again, that's why you also have that nice chart of numbers you get to use. And remember, if we were face to face, you wouldn't get to use anything. Let's see if I find another one like that. Okay, so at the end of the homework, they're just kind of running you through a whole bunch of different, problems. Looking at that one, what would the answer be? Just by looking at it, what would the answer be? This one is a quadratic, so this takes you back to chapter 11. This is a quadratic problem. And this is a nice linear problem, taking you back to basically algebra 1. This one, you get a common base, and our last example is going to be this one, because it's a fraction. So 1/4 equals 2 to the 6x. 1/4 equals 2 to the 6x. So you look at your numbers. Down here, there's a 4. Up here, there's a 2. 4 and 2 are both powers of who? That's an easy. 4 and 2 are both powers of?
2?
2. 4 and
Yes.
2 are both powers of 2. But here's the problem. This is not 2. This is actually 1 over. It's in the denominator. 1 over 2 squared equals 2 to the 6x. That's not a common base on both sides. When we say a common base on both sides, they have to both be in the numerator. They have to be right across from each other. I don't have, over here I have 2 to the 6x, but over here I don't have a 2 to that power. I don't have a 2 to something. I have a 1 over 2 to something. So what you have to do is you want this on the left side, you want it to be a 2 to a power. So how do I raise this upstairs?
Doesn't it have to be a negative?
Exactly. It's 2 to the negative 2 if I raise it upstairs. Now I have the same base. So all that means is you can flip a denominator back up by changing its exponent to a negative. See, that's why if you don't understand the properties of the exponents that we did in chapter 10 and know how to manipulate positive and negative exponents, if you didn't actually do that, you're going to be kind of lost with what we're doing here. Because this is part of the work you have to show. Now you can let this exponent, negative 2, equal that exponent, your 6x. Divide by 6. And we get x equal negative over a positive is a negative. 2 over 6 is 1/3. So x is negative 1/3. If you plug it in, 2 to the 6 times x. 2 to the 6 times negative 1/3. So that positive times that negative is going to be a negative. And 3 goes into 6 2 times. 2 times negative 1, that's 2 to the negative 2 on this side. And 2 to the negative 2 would be 1 over 2 squared. And 1 over 2 squared gives me 1 over 4, which is that side. If you plug it in and check it. And that's 12a. That's the homework for 12a. Negative 1 over 3. So we did, what did we do? We did 7 out of the 12 problems there. As examples. And as we get ready for 12b, sorry, I'm giving you the close-up of my ugly mug. 12b has 54 problems because here's the deal. What happens when you come across a question that looks like this? When it's 2 to the x equals 8. We have the technology. We can solve this because all you got to do is rewrite it. 2 to the x, 8, that's a nice 2 to the 3rd. So you got your x equal to a 3. Happy days. But what happens when you have 2 to the x equal to a 7? Now we don't have the tools to do this. 7, it cannot be written as a power of 2. There is no way to change, and you can't change 2 to any other base. 2 is a prime number. That's as low as it's going to go. 7's a prime number. There is no way I can write 2 or 7 as an exact power of a 2. So there has to be some other way to do that kind of a question. So, now I get the board ready. I notice a few of you have not even, I don't know why some of you do the direct message, because all you do is make sure that now I'm in the direct, I always forget that I'm going to, yeah. Okay, that's all right. If that's your thing, then that's your thing. Make sure you do your chat check right now. I'll get this ready. Here's another one with the direct messages. That means it puts me in direct message. Messing with me. I don't know if you're a witness protection or what. All right. When we first started solving equations, we basically had to come up with inverse operations for the operations that we had in place. When we had x plus 2 equaled 5, inverse operation, subtraction, subtract 3 from both sides. If it was minus, then we had addition. If it was 2 times x, then we have division. If it was x over 2, then we have multiplication. Don't worry about how fast I'm going. I'm just showing you that every time that we have an operation, there's an inverse function. There's an inverse operation, something that undoes it. So we can solve for x. What divided by 2 gives me the 5? 10 divided by 2 is the original 5. What undoes division? Multiplication. We have that inverse function, that inverse operation. And then we get a little more sophisticated. Just in the last chapter, you had square root x equaled 8. And some of you were supposed to show the work. How do you undo a square root? You isolate the radical, then you undo the radical. You have to square both sides. By squaring both sides, that creates a perfect square here. That gives me the x. Over there, you get your 64. You just show the work. And then you make sure you check your answer. If it's a cube root, then you have to cube both sides. And that gives us a 512. The inverse operation for a radical is an exponent. But what we don't have is an inverse operation to an exponential equation. Division is not going to undo an x when it's up here because it's not multiplication. Division doesn't undo this. Multiplication doesn't, addition, subtraction won't. Yeah, let's take the xth root. Certainly the xth root will undo this, because when you rewrite this, this is 2 to the x. The xth root is the 1 over x power. That is 2 to the x, whoops. That is 2 to the x over x, and so that is 2 to the first. Yeah, that's 2. But over here, all you did was move it around. Now this is the x root of 7. Remember what you're trying to accomplish. You're solving for x. What you want to know is, what does x actually equal? You want to get the x out of the exponent and bring it down in front so you know what x actually does equal. You want to get x out of its exponent spot. So, along comes a Scotsman by the name of Jean Napier, or John Napier. Not that this will be on your test, but his name is John. I used to think he was French, but turns out he's Scottish. And if it's not Scottish, it's crap. And he discovered logarithms about the 1400s, 14 to 1500s. Logarithms is the notation that we use to undo exponential equations. So here's how it works. Just like you had radical form. And you are supposed to be able to convert that backwards and forwards into exponent form in chapter 10. The nth root of a to the m is a to the m over n. You needed to know how to convert this backwards and forwards. You're going to need to know how to convert logarithmic form backwards and forwards into exponential form. And that's what we're giving you right here is the logarithm is the inverse function to an exponential function. And again, what that means they undo each other. A logarithm undoes an exponential function, and an exponential function will undo a logarithm. So the logarithmic form looks like this. Log, L-O-G. And I know that everywhere else I've seen it, they don't use capital L. They use lowercase l. But I have seen students confuse that lowercase l, and I don't know why, but they write an I. When they read it in the book, they think they're looking at an I. And I go, how in the world are you spelling logarithm with an I? Drove me crazy. So I have always written it capital L. Log. Base B. Log. Base B. Of X. Of X equals Y. Log base B of X equals Y. We're taking the logarithm base B of something X, and it's equal to some value Y. So it's a logarithm base B of something X equal to Y. That base B is a subscript. It's like when we write the slope of a line is Y sub 2 minus Y sub 1 over X sub 2 minus X sub 1. They're at that's at the foot of the G. That's at the foot of the Y. That's at the foot of the Y. Subscript, like a submarine, it's below. A subway, that's below. Now there's some restrictions. Logarithms do have the restrictions. That base B, the B has to be greater than 0. It has to be a positive number. So it cannot be negative and it cannot be 0. Also, the base B cannot equal a 1. You can't have a base 1. Everything else is fine. You can have fractions. You can have a base 1/3, 2/3. You can have a base of 18. You can have a base of 1.7. You can have any real number as long as it's positive and not a 1. Inside the logarithm right here, this X has to be greater than 0. It has to be positive. You cannot take the logarithm of a negative number, and you can't take the logarithm of a 0. You can only take the logarithm of positive numbers.
And why is that?
That's inside the logarithm, what you plug into logarithms, the X.
Yes, but why can it only be positive numbers?
You'll see when we actually translate it.
Okay, okay.
Wait, here. If you try to take the logarithm of a negative number, it's undefined. It won't work. If you try to take the logarithm of a 0, it won't work. It's impossible. There's no way it'll happen. But anything greater than 0, perfectly fine. And then last but not least, Y can be any real number. Y can be anything and everything. Y is any real number. Y can go from negative infinity all the way to positive infinity. So now, Here's how we translate. And, you know, I don't, and maybe if I did, I would feel better. But if you are a person who does meditation, when you meditate, you have something called a mantra. You know, you sit on the floor, you get into your happy place, and you do it whether it be a or you do some kind of mantra that you chant or you just say that where you repeat that gets you into that nice transcendental state of meditation. This is your logarithm mantra. This is how you will convert logarithm into exponential. This is how it works. Log base b of x equals y. Base b to the across y, base to the across, equals what's inside x. Base b to the across y equals what's inside x. This is what it looks like in exponential form. So this is how we convert. Base b to the across y equals what's inside x. The base b of the logarithm all the way to the across equals what you got inside the x. And that's how you convert log form into exponential form. And the way you convert it back is I would just kind of rework the mantra backwards. It takes a little more effort, but coming down from transcendental meditation, it does take a little more effort. The rules that we establish over here are the same over there. Over here, the base in exponential, that base still has to be greater than 0, cannot equal a 1. The x, no matter what, that x is going to be greater than 0. Is always going to be a positive number. And y can be any real number. So this over here, 2 to the x equals 7. The answer, because you would solve for x. Basically, you're going to fill in these blanks. Log base somebody of something equals something across. You got to fill in those 3 blanks when you want to convert that exponent form back into a logarithm. So over here, somebody converted my logarithm into an exponent. Somebody converted my logarithm into an exponent. In other words, somebody already did base to the across equals what's inside. So where does that 2 gonna go over here? Is it the base, is it the inside, or is it the across? Where does the 2
Could be
go?
across.
So remember, what I have over here is base
Okay.
to the across equals what's inside. So
Could
the
be
2,
Would it be the equals or equals the x goes?
the base of the logarithm
If they
is always the base of the exponent.
So then 2 is the base.
So 2 is the base.
Okay.
So since that base is a 2, the base of the logarithm, base of the exponent, always the same thing. Base to the across. So base to the across. The x is my across.
Mhm.
Equals what's inside. What's
7.
inside is my other side. So 7 is over here. So what is this x equal? This x is equal to log base 2 of 7. And that would be something that we could actually answer on a calculator. Or back in the good old days, you would have to look them up in huge textbooks of tables of numbers, because those numbers would already be calculated for us. But what you have to learn is how this formula, how this translates backwards and forwards. So what I usually do when we are in, the same room with each other, everybody's in one happy face-to-face place, I have everybody say it all together. So I got everybody's out. I got nobody showing their faces. I got no microphones on. So let's get some microphones on, whether you show your faces or not. Repeat after me. You ready? I want some microphones on. Give me some microphones. I got 2 on, 3.
The pool keep on popping up. Is
Let's see, who else? Anybody else? Look at all the rest of the chickens. I'm recording this, so I know who the chickens are. I know who the ones are probably out watching the stories right now, watching Price is Right. Here we go.
Yeah. The
Base,
pool keeps on popping up.
right after me. Base B
Base B
to the across Y
No, but
to
Guys,
the
it's
across
Y.
Y
equals what's inside X.
equals what's inside X.
One more time.
Base
Base
B
B to the across Y
across Y
equals
equals
what's
inside X.
inside X.
Well, what's inside the egg?
Wow. Look at, we got 1, 2, 3, 4, 5, 6, 7, 8, 9 people who are not even participating. I'm going to have to do something about it. Okay. Seriously. I can't wait till this whole
152 times 1.
teach from home thing is over. So the first set of problems on the homework.
It's in 152. Yes, it's going to be that big number.
So right here, all you're doing is write as an exponential function. So you're supposed to convert this into an exponential function. In fact, if you look at the review sheet, question 11, question 12, question 13, question 14, question 11, change this into a logarithm. Question 12, write this as a logarithm. 13, write this as an exponential function. Question 14, write this as an exponential function. You're not doing anything but converting. Basically, your entire chapter 12 is going to be dependent upon whether or not you can convert. You got to get out there and convert them. Almost sounds like you're going to be going out on, working the campaign trails and converting people. Democrat to Republican, Republican to Democrat. I don't know. So here we go. So base 5 to the across 3. So as an exponent, 5. And then here's the exponent button, superscript, 5 to the 3rd, base 5 to the across 3 equals what's inside 125. That's all you do. On the second one, I'm not going to type it in, but 7, base 7 to the across -2 equals what's inside 1/49. Base to the across equals what's inside. And over here on this one, number 4, you're not even really solving. It's just write it as an exponential. They don't even want you to do the final answer. 8 to the 3rd equals what's inside x. 8 to the 3rd equals what's inside x. They don't even want you to simplify 8 to the 3rd. Leave it as an exponential notation. Okay? Don't get frightened by looking at pi. Pi is good for you. The logarithm over here on the far left, log, there's a little subscript, pi. Log base pi to the across -2. Pi to the -2 equals what's inside this 1/pi squared. Okay, so at the foot of the G, that's the base of the logarithm. Log base pi to the across on the other side of the equals is -2. So pi to the -2. So right here on your toolbar is a pi. Exponent, we put a -2 base to the across, and then equals what's inside is 1/pi squared. 1/, and in the denominator you have a pi squared. And that makes perfect sense because if you have pi to the -2, you would flip it down and it would become pi to the +2. All right, this one. Okay. Base is 3, log base 3 of the 4th root of 3. That's the 4th root of 3 equals 1/4. Base B, so that's log base 3 to the across 3 to the 1/4 equals what's inside 4th root of 3. 3 to the 1/4 equals 4th root of 3, and that's absolutely true. Now you're supposed to write this as a logarithm. So you're supposed to convert this into logarithms. So let me pick a different one. Here's a good one. 10 to the 6th is 1,000,000. Ten to the 6th power equals 1,000,000. And what we want to do is we want to write it as log base something on the inside equals something over here. So remember what happened. Somebody took my logarithm form. They did base to the across equals what's inside and got this. So we're staring at base to the across equals the inside. Somebody converted this into base to the across equals the inside. So for my logarithm, what's the base?
1,000,000?
Would the base be 10?
What's the base of the exponent?
Oh, 10.
10.
Remember, they're the same thing. The base of the logarithm and the base of the exponent, they're both, that's where the b goes. We're staring at base. This has already been converted into base to the across equals the inside. So when you put them back where they came from, this is base to the across. So where's the 6 coming from? Is it the inside or is it the across?
Across?
Across.
We went base to the across. Base to the across, and up here, 10 to the 6th. That's the only place where you're going to have your exponent. Base to the across. So here's the base, and this is always the across. When you convert it, right? Base to the across. So the 6 goes over here. Equals, and then what does it always equal? It equals what's inside. So the million goes back on the inside. That's how you put it back together. So here's how you got to type it in. So there is no actual LOG button to click on. So you just type on the keypad, LOG, and I hit I instead. What am I doing? LOG, and I want base 10. Well, look at your toolbar. This is superscript. That's going to give you an exponent. But if you go a few more down, here is the subscript, log base 10. Log base 10 of a million. Now, if I try to just type in a million right now, that million is going to be in the base position. So I can't type it there. What I have to do is either use the mouse and click up, or just use the arrows, and I just move my arrow to the right, and now I can type in my million. There it is, log base 10 of a million. And then equals what's inside, which is a 6. Log base 10 of 1 million is equal to 6. So if I write this one, log base something of something equals something. What's the base?
Would it be pi?
Yep.
Mm-hmm.
The base of that exponent is pi, so this is log base pi. So pi goes in the base position. So log base something, pi, base to the across. So 12 is going to be my across. It's across on the equals. Base to the across equals x is on the inside. So log base pi of x equals what's inside, or sorry, base to the, I got ahead of myself. Base to the across equals what's inside, equals what's inside. So x is on the inside, and then base to the across. Across is where the 12 goes. Honestly, before you type this in, you might want to write it down on paper. You're going to have to do it for the test anyway. But as you can see, there's not a lot of work to show, because all you're doing, especially when it comes to when you look at these questions on the review sheet, just change that into a log form. Change this into a logarithm. Change it into a logarithm, so on and so on. So now 12. Find the value of this logarithm. What does log base 6 of 36 actually equal?
Would it be 6?
Well, let's see. Let's see. And I know I can certainly understand why you're saying 6. But remember, this is about exponents. Log base 6 of 36. So you say 6. Let's test it. If we test the whole proposition, base to the across, 6 to the 6th power equals what's inside 36. So your guesstimation was a 6 to the 6 equals 36. Well, 6 times 6 times 6 times 6 times 6 times 6, is that going to be 36?
No, it would be, wouldn't it be 2?
Exactly. The question that is being asked right here, when we see log base 6 of 36, the question that a logarithm asks is 6 to what power? 6 to what power makes 36? Exponents. You got to think exponents, not multiplication. It's exponents. 6 to what power makes 36? So this is where I get to tell the same joke that I've been telling for, I don't know, 30 years now teaching. I am currently, since both of my parents passed away. My mom passed away 2 years ago on her 97th birthday, 8 a.m. on the day of her 97th birthday. I guess she figured she'd get more attention that way. I don't know. That was my mother. Anyway, my wife and I are currently living in the house that I grew up in. I'm currently sleeping in the same bedroom that I grew up sleeping in, which is bringing back incredibly strange, weird feelings for me. But be that as it may. Growing up here in this neighborhood, about 5 doors down, lived Richard and Manuel Hernandez, and their father, Manuel Sr. And I remember being about 9 years old, and he asked me a question, and I said, I don't know. And that's when he told me, you know why Mexicans have such huge shoulders? And I said, I don't know. And he said, that's right, because they keep saying, I don't know. I usually get laughs, but you guys are obviously not even, you're either offended or you didn't think it was funny. Anyway, I guess I should stop telling that joke. Anyway, or I should just keep my day job. Anyway, log base 6 of 36. What does that equal? I don't know. That's what you do. I don't know what it equals. Let's call it X. Call it something. You can't solve an equation if you don't have a variable. That's the whole idea. You can't solve it if you don't have a variable. Now you can convert it because they're not always going to be this obvious. Now you can convert it into its exponent form. Base to the across, 6 to the x. Now you can see what you're dealing with. Equals what's inside, 36. And it eliminates that initial guess, that initial reaction. 6 to what power is 36? Now if you can see, hey, that's going to be a 2. X equals 2. That's fine. Well, remember the way we solve this is we get a common base on both sides, 6 to the x over here, 6 to the second. So therefore, this x has to equal that too. Log base 6 of 36 is 2. That's what variables are for. When we don't know something, we use a variable. Then we can solve. Really? Log base 64 of 4. They're not always going to be super obvious. Log base 64 of 4.
You sound like a robot.
Okay, fix it. All right, how's this?
Better.
Okay. So 64 to what? Okay. I don't know. X. Base to the across equals what's inside. 64 and 4 are both powers of? (64 and 4 are both powers of?
4.
4. 64 is 4 to the third to the x. And don't forget 4 to the first. On the left, 4 to the 3x. 4 to the first. That's where we get 3x equals 1. And then divide by 3. So the answer, x is 1/3. Log base 64 of 4, 64 to what power? 64 to the 1/3 power is how you make a 4. It's always converting. Convert, convert, convert. Okay. Special properties of logarithms. That next question was number 16. Log base 11 of 1. So, I don't know, let's call it x. So when you convert it, base 11 to the across x equals what's inside 1. So on the left side, you have an 11. On the right side, you have a 1. Looking at your chart of all your exponents, what power, what exponent makes something into a 1?
Is it 1?
Well, 11 to the first would just be an 11.
Is it because it's 11 one time?
No,
Okay.
but made sure I put it on there. There's an exponent that always generates ones.
Wouldn't it be 0?
Exactly. In fact, I believe it's rule 6, exponent rule 6. Or actually, 7. A to the 0 is equal to 1 as long as A does not equal 0. Everything to the 0 power is always 1. Do you remember that?
Yes.
Yeah,
Yes.
I remember.
Okay. So what power is going to change 11 into a 1? 0 power.
Okay.
The exponent has to be a 0. So on this side, you could change this to 11 to the 0 if you wanted to. So this x would have to equal a 0. What if I change this to a 5? Log base 5 of 1. 5 to what power is 1? What would the exponent have to be?
0.
1
Still have to be
or
0.
0.
It would still have to be a 5 to the 0 to make a 1. What if I change it to an 87? 87 to what power makes a 1?
0.
It still has to be 0. So guess what? No matter what your base is, if you take the logarithm of 1, the answer is always 0. Log base b, no matter what the base is, of 1 always equals 0. Whenever you take the log of a 1, you always get 0. Always, 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 always. The log of 1 is always 0. Now, wait a second. I thought you said it couldn't equal 1. The base can't be a 1. Wait a minute. I thought you said something that couldn't be 0. The base can't be 0. Inside here can't be 0. Over here, you could have any number you want. So we're not breaking any rules. But if you take the log of a 1, it's always 0. The next rule. Remember this idea. Logarithms and exponential functions are inverse functions. And that means they undo each other. So the next property is log base b of b to the x power. So in other words, if I had log base 5, and then inside, I'm taking 5 to the third power. So let's just say, what does that equal? Let's go with the whole, I don't know, let's call it x. If you convert this base to the across, what's my base of the logarithm?
The 5?
5. What's the across?
The 3. No.
5.
All the way across.
Oh, x.
5 to the across. 5 to the x equals the whole, what's the whole inside?
5 and 3, 5 to the third.
5 to the third. Base to the across equals what's inside. What does x end up equaling? You see that?
Yeah. Well,
I mean, it's a short, sweet, and done, because this is already a base 5.
oh, I see.
You're taking a logarithm, base 5, and inside you have an exponent, base 5. Exponential functions and logarithms, if the bases are the same, they're going to undo each other. This log base 5 is going to undo this exponent base 5. So guess who's coming out? The 3. That's its job. It's going to undo that base, and we're going to get a 3. So log base b of b to the x is just going to equal the x. Log base b of b to the x power. This log base b undoes the exponent base b. They undo each other, so we get the x. Because they're inverse functions. That's the whole idea. They're inverse functions of both sides. So when you have that 2 to the x equals 7, and you're trying to solve for x, you're trying to undo a base 2. And we want that x out of there. Since that's a base 2, you would take log base 2 of both sides. Because the only thing that's going to undo an exponent base 2 is a logarithm base 2. In order to undo an exponent base 2, you need a logarithm base 2. Logarithm base 2 of 2 to the x is just that x. It undoes the exponent. And what do we end up with? The answer is log base 2 of 7. And that's the exact value of the answer. That's our exact answer. It's also what we got when we converted it. And we undid our base to the across equals what's inside and put it back into the logarithm. But that's the whole idea. It also works for this. Number 3. Base b to the raised to the power of log base b raised to the power, so raised to this logarithm power of x. So I have an exponent, an exponent example here, base b raised to a logarithm power. So you might have something like 5 raised to a logarithm base 5 of a 9. Well, since this exponent is base 5 and it's raised to a logarithm who is also base 5, since the bases are the same, they undo each other. And if they undo each other, this is going to be my answer. That's an exponent base 5. That's a logarithm base 5. They undo each other. So the answer is 9. B to log base B of x. They undo each other. You just get the x. So you need to recognize what you're looking at. And there's no work to show. You just need to know that that is exactly an example of what you're looking at. And anytime you have something this uncomplicated, log base 12 of a 12. Log base B of just B, log base B of itself. If we don't know what it is, you can always do base to the across equals what's inside. Base to the across equals what's inside will always set you free. I don't know, let's call it x. Base to the across, 12 to the x equals what's inside, 12. What's this exponent on the right? This would be 12 to the what, if it's just a 12?
To the 1.
Be a 1. So 12 to what power is the 12 on the inside? 12 to the x would have to equal a 1. So anytime you have a logarithm base B of itself, the answer is 1. And those are properties where if that is what you're staring at, the answer requires no work whatsoever. I mean, when you look at the review sheet, that's why I put these on here specifically, number 18. That's base 7 to a logarithm base 7 of 2. The exponent is a base 7 raised to a power log base 7. Since the bases are the same, the answer is just what?
1.
It's not log base 7 of 7. 7 to log base 7 of 2. So we're talking property number 3. Look at property 3. 7 to log base 7 of a 2. 7 log base 7, and that's my 2. So what's the answer? This base 7 undoes the logarithm base 7. There's no work to show. You need to know the properties. Number 23. You see how that's log base 2 of 2 to the x plus 3 equals 17? On the left-hand side, what happens to log base 2 of 2 to the x plus 3 since the bases are the same? It's a log base 2. Inside you have 2 to the x plus 3. What do you end up with? Just what?
I have no idea.
I'm probably asking something a little too quickly. Okay, what if we did base to the across equals what's inside? 2 to the what?
Be 2 to 2?
No,
Ah,
2 to the 3.
to the across.
Oh,
Base
Oh, it's 17.
2 to the 17 equals 2 to the,
2 x
X plus 3.
and then do you have the same base? Yeah, 2
Yeah.
to the 17 and 2 to the x plus 3. So then your x plus 3 is equal to 17.
Okay.
Okay, but what I was getting at was on this side, on the left side,
Mhm.
that is log base 2 of inside 2 to the x plus 3. Since the bases are the same
Mhm.
on this left-hand side, this is just x plus 3. Over here, 17. Because they undo each
Okay.
other. Okay. So log base 11 of 1, that's a 0. Log base 9, and inside 9 to the 4. Should have had an answer like 18 seconds ago. It's a logarithm base 9 of 9 to the 4th.
4?
That's 4. That's an exponent base 3 raised to a logarithm base 3 of 9. So since the bases are the same, the answer is just
9.
9. Okay, this one, when you're, let me see another one. Okay, these properties. So the last little bit, properties, is the reason why Jean Napier came up with logarithms is to actually make math simpler. Yeah, right. But actually to make mathematics, to make calculations simpler. Because of logarithms, multiplication becomes an addition problem. Division can become a subtraction problem. And exponents can become a multiplication problem. Because of logarithms, the operations of multiplication, division, and exponents, actually, they take a notch, they take a little step down in difficulty. Here's the rules. The rules of exponents, there's 3 of them. And remember, these equals go both ways. The first one, if you have log base b of multiplication, m times n, two things multiplied together, then you can split it up. You can split multiplication into an addition problem. It's log base b of m plus log base b of n. You can separate multiplication into the addition of the two logarithms. So multiplication is now the addition of their logarithms. Number two, if you can split multiplication up with addition, then it makes sense that you can split division. You can split up a division problem with subtraction. Log base b of m over n is log base b of m, the numerator, minus log base b of n, the denominator. So you can separate this into the subtraction of the two logarithm values. And the third one, I made a little crack earlier about the Price is Right. The third one I like to call the Price is Right property. Log base b of m to the x power. An exponent. So raising something to an exponent, I like to call this the Price is Right property because that exponent can come on down. That power is now a multiplication problem. It's x times log base b of n. So instead of an exponent, m to the x power, it's now a multiplication problem, x times log base b of n. So in other words, 2 to the x equals 7. Now, I'm not going to get into the whole, because I'm not going to ask you to do any calculator work on this at all, on this test at all. But calculators have never been capable of doing all the different bases. Calculators have only been really capable of doing two separate bases with logarithms. So if you look at this calculator on the screen, you have only two logarithm buttons on a calculator. This one, LOG. That LOG button right above it has in blue is 10 to the x. Let me see if I can blow this up a little bit. And I don't think that's going to do us any good because now you can't see it. Never mind. So that LOG button is a logarithm base 10 automatically because it is associated with the 10 to the x right above it. So if I hit this button, it's a base 10. Down below this LN, LN stands for the natural logarithm. Why don't they write it NL instead of LN? Well, because I used to think Jean Napier was a Frenchman, I used to think logarithms au naturel for natural logarithm, because that's how the French would speak. So that's what I'm going with. I don't know the real story. So that's the natural logarithm. The natural logarithm is a base E. E is the natural logarithmic number. If I go like this, second e to the first power, e is the irrational number, 2.718281828, but it doesn't repeat a pattern. There is no last digit. It goes on forever, on and on and on. It's an irrational number, just like the number pi. but it occurs forever and ever, all over nature. From the seeds of a sunflower to the conch shells, it's all over nature. In finances, E props up in finances all over the place. When you take things to an infinite amount or infinitesimal amount, out pops the number E, the natural logarithmic number. So the natural logarithm undoes an e to the x, and the common logarithm, log, undoes a 10 to the x. Since these are the only two buttons I could press on a calculator, then when I would do this kind of a question right here, I would only take, for instance, log base 10 of both sides, because that's the only kind of button I could press on a calculator, because I would want to plug it in on my calculator. But what that allows me to do is Price is Right property. Come on down. This is now x times log base 10 of 2 equals log base 10 of 7. Now I have a multiplication problem. Now I know how to solve for x. To solve for x, I divide both sides by log base 10 of 2. So x would equal the log base 10 of 7 divided by the log base 10 of 2. Then I would punch each of those into the calculator, and my answer would be, and again, this is not going to be on your test, I promise. I'm just showing you how it does work. I would go the log of 7 and then hit divide by the log of 2, and I hit equals, and that's the answer. 2 to that power gives me exactly 7. And I can show you if I go 2 to the, and then I'm going to go answer, 2 to that answer, I get 7. 2 to the 2.80735499922, that gives me a 7. But here's what you got to do. You have to be able to put these two together as a single logarithm. This is number 34. Log base 5 of 18 minus log base 5 of 3. You want to write it as one logarithm. So how do we put subtraction back together as one logarithm? You divide. So this is one logarithm, base 5 of 18 over 3. Can you reduce 18 over 3? What's 18 divided by 3?
6.
So the final answer is just log base 5 of 6. And that can't reduce any further. There's no final. That's 34. This is 39. Log base 9 of the 5th root of y. Directions say use the power property, which is the Price is Right rule. none of this works with radicals. So you have to convert your radical into an exponent. So this is log base 9 of y to the what? What exponent is a fifth root? What's the exponent for a fifth root? See, this is why I question whether, about the whole chapter 10 test. Maybe I need to go back in and regrade those. Y to the,
1/5.
thank you, 1/5. Then they want you to use the exponent rule. Price is right, come on down. So if you have an exponent here, it comes down in front. So come on down. This becomes 1/5 times log base 9 of y. That's all. Number 42, they want you to separate the logarithm. So we did one where we put it back together and made back into one logarithm. Now they want us to take it apart. 42 is log base 4 of x to the 5th over y. So it's kind of like if you were away at college and you and your roommate were living in some kind of weird, somebody had the top floor, somebody had the bottom floor, and now you're moving back home after the spring semester. The first thing you would do is you would separate from each other. How would we separate division? Which one? Would it be addition, subtraction, or Price is Right rule if it's division?
Subtraction.
Subtraction. So it's log base 4 of x to the 5th minus log base 4 of y. Then, what do you do when you finally get home? You gotta unpack your bags. Come on down. 5 times log base 4 of x minus, well, it looks like y left everything in the dorms. So there's nothing to come on down, just log base 4 of y. So they want you to separate this into a simple log base 4 of x and a log base 4 of y. So no exponents. That's all. So one last example I want to show you, and I'm going to let you guys get out. It starts at number 44. So in 44, this is actually how it used to go down. On 44, you're given log base b of 3 equals 0.4. And log base b of 6 equals 0.6. And they want you to give an answer for log base b of 18. The only thing you have to work with, the only thing you know for log base b is 3 and 6. So can you use a 3 and a 6 to make an 18?
Yeah, I mean, yeah, 3 times 6.
3 times 6. So this is log base 3 of 3 times 6. Because that's 18. How would we separate multiplication?
By adding.
By addition. See, in the old days, not when I was alive, there wouldn't be an 18 in the back of some book. You would have to make the 18 out of pieces. Now you can look up log base 3 of 3 plus log base 3 of the 6. Because that's what you've been given. Log base 3 of the 3, that's 0.4, plus log base b of the 6, whoops, these are b's. Log base b of the 6, that's a 0.6. So the whole thing is 1.0. And they made it easy for you because what they probably should do is not even tell you the 6. They should have told you 0.2 or a 2, because then you would have to go a 3 times a 3 times a 2 and split it up into 3 things. But that's it. That's all the chapter 12. So you have your 12A and your 12B. You got your review sheet. I'm going to send an invite to Wednesday's review session if you would like to attend. You can always watch on, go into the playlist and watch their review session if you want to. But then you'll have your review session. Any questions you want to ask before the tests start on Thursday. Again, the quiz is optional today. If you choose to submit the quiz by 11:59 p.m. tonight, that means it will be graded and it will go into your overall grade and your quiz grade. There are no takebacks. Now, if it's your lowest quiz score, if it's one of your lowest quiz scores, yes, it would be one of the ones that get dropped out of the 2. But you cannot, turn it in and then later on say, you know what, I don't want that one. Once you submit it, it's going to count. All right. Any questions before we check out?
Okay. 11 and 12 are home test. Okay.
Yep. You'll have from 10:45 until 11:59 that night. Like I said, chapter 11 is 6 problems, and chapter 12 is going to be no more than 14 problems, I said.
All righty.
Okay.
All right. Thank you.
All
Bye,
right.
Mr. Esquivel.
But
See you.